Hello, my name is Fateme Baneshi. I'm a third year PhD student under the supervision of Professor Manuel Soler. And in this video, I'm going to briefly present my PhD thesis, which focuses on climate optimal aircraft trajectory planning at network scale. This presentation is divided into four parts. First, I'll give a brief introduction to the problem, methodology, and then I'll present some advances and results, and finally, outcomes and plans for future. Let me start with the motivation. Aviation is one of the contributors to global warming through the emission of CO2 and other non-CO2 species. The climate impact of non-CO2 emissions has been claimed to be 2 times higher than the impact of CO2, and they are strongly depend on the atmospheric conditions and time of the emission. Therefore, climate-aware trajectory planning has emerged as an operational strategy to mitigate the climate impact of aviation. However, there are some research questions which need to be addressed. For example, is optimizing individual trajectories feasible from the operational perspective? How these individually optimized trajectory affect the performance of ATM system? What are the challenges of adopting these optimized trajectories? Here we can see two different sets of trajectories. The first one is shows the trajectory of business as usual flight, and the right hand side figure shows the climate optimal trajectories. The light gray areas show the climate sensitive areas. That meaning that if we fly through this area, the climate impact will be increased. Therefore, to mitigate the climate impact, we need to avoid these sensitive regions. Uh, Such behavior change the traffic pattern in specific areas, which can lead to capacity demand imbalancing, increasing in workload complexity, and the number of conflicts. Therefore, we need to solve this problem at the network scale and be aware of the consequences of adopting climate optimal trajectories at network scale and try to compensate for these negative impacts. Our methodology involves multiple steps. First, we optimize each individual trajectories in a climate-friendly manner. After optimizing individual trajectory, we integrate this trajectory into the network level and assess their performance in terms of air traffic complexity, demand, and conflict. And finally, we try to propose a resolution strategy to compensate for the negative impacts, if there are any, to deliver a climatically oriented aerial traffic. Such resolution strategy can be modeled as an optimization problem with multiple objectives. The objectives of this optimization problem includes the complexity of the traffic, the demand, workload, number of conflict, and closeness to the climate optimal trajectories. Different decision variable can be considered in this problem to achieve these objectives. And the problem can be solved using mathematical programming, learning-based approach, or heuristic approaches. Actually, heuristic approaches are some optimization methods which are proper to simplify the complexity of the problem by focusing on relevant aspects. However, the execution time in this method will be scaled up with the number of aircraft involved, and they need to be performed from scratch whenever the scenario change or new sets of trajectory are received. In contrast, reinforcement learning reallocate the process of resolution from centralized point to individual aircraft. Each aircraft can take action to maintain the manageability of the traffic with fast execution time and independent of the traffic scenario and weather condition. It means that the obtained policy can be applied to any unseen scenario. Basically, in the framework of reinforcement learning, an agent interact with an environment. the agent receives the current state of the environment, perform an action according to a policy. The action is applied to the environment, and the environment transits to the next state and provide the agent a feedback reward. The final goal is to find the policy that maximizes the future expected reward. Uh, in this respect, and due to the potential of the reinforcement learning to solve real world problems, we use these algorithms to tackle this problem. To solve the problem of resolution, we use the framework of multi-agent reinforcement learning. The environment is aerospace. The agents are aircraft interacting in the same environment. The state space is aircraft information, as well as the information of the surrounding traffic. And the action space could be aircraft speed, altitude profile of the aircraft, or their lateral route. And the reward function includes conflict, complexity, and adherence to the climate optimal trajectories. Uh, Within this framework, each agent receives a local observation or a global observation of the environment. Accordingly, takes an action, the joint action of all agents applied to the environment, and the environment transit to the next state and provide each agent with a feedback reward, which this feedback reward and the state shows the complexity, the conflict, and any other indicator that we considered in the reward function. Uh, to see the performance of the reinforcement learning to solve this problem, we considered a case study, the traffic over European airspace on 20th of December 2018 from 12 to 14 within the free routing airspace. All the trajectories are optimized individually. The objective function for the optimization is the weighted sum of the operational cost and climate impact. We can see that by increasing the weighting parameter of the climate impact, the traffic pattern will change. The first figure shows the cost optimal trajectories, and this figure shows the climate optimal trajectories. To see the climate impact of these different sets of trajectories, here we depicted the climate impact associated with individual species. We can see that by assigning higher weights to prioritize climate impact, we reduce the net climate impact, which mainly achieved by generating cooling contrails, the blue bar. To show the generation of contrail, here in this figure, we show the formation of persistent contrails along trajectories. We can see that for the set of climate optimal trajectories, we promote the generation of cooling contrails and reduce the formation of warming contrails. To see how this mitigation affect the performance of the air traffic system, we showed the location of potential conflict for different sets of trajectories. We can see that by accepting trajectories with less climate impact, we increase the probability of collision in specific areas and flight levels, which these areas correlated with the area that the cooling contrail are generated. Therefore, a strategy is required to deliver a manageable aerial traffic. Because in the end, the air traffic management system may refuse to accept these trajectories because they might adversely affect the manageability, or they might not be acceptable from the operational perspective. To solve this problem, we propose a resolution strategy based on reinforcement learning. Within this framework, the aerospace is a free routing aerospace, which means that we have continuous space. The status space is aircraft speed, heading angle, and the information of the neighboring aircraft, such as their speed, their heading, minimum distance, and from other aircraft. The action space is aircraft speed, and the reward function includes conflict and closeness to the climate optimal speed. We used a multi-agent twin delay deep deterministic policy gradient method to tackle this problem. When we apply the proposed resolution strategy to solve this problem, here we can see the relative difference of the number of potential conflict from the cost optimal trajectories. We can see that the orange bars show the difference of the number of potential conflict before applying the resolution strategy, and the green ones show the conflict after applying the resolution. We can see that we can successfully resolve a high number of conflict for the set of climate optimal trajectories. And also, we assessed the climate impact and also the operational cost before and after applying the resolution strategy. We can see that the proposed conflict resolution strategy can achieve a balance in the ATM system by enhancing the manageability. It means that reduce the conflict with a slight compromise in the operational cost and climate impact. For example, for these sets of trajectories correspond to EI 0.01, we can achieve approximately 60% mitigation in the climate impact at 1% extra cost and without negatively affecting the manageability of the air traffic or increasing the potential conflict. To have a visual understanding of the performance of the resolution strategies, we showed the conflict map of different sets of trajectories. We can see that the proposed resolution strategy can reduce the air traffic complexity, especially in high density areas. For example, for the trajectories with less climate impact, we can have to some extent manageable air traffic. Of course, the algorithm cannot successfully resolve all the conflict in the aerospace because the only decision variable in this problem is a speed profile. And we expect that by including other decision variables in the problem, we can increase the potential of this problem. Also, within this framework, we only consider the number of conflict within the objective function of the reinforcement learning. However, we need to integrate also air traffic complexity into the objective function and also incorporate additional decision variable such as the lateral path or the altitude profile of this trajectory. Here are some outcomes of this research during these 3 years. And I wanted to thank you for your attention. And please do not hesitate to contact me via this email if you have any questions or if you are interested in this topic.